Next in our discussion of rational functions is how do we come up with sketches for rational functions. Some key pieces of information for rational functions are the y-intercept. You find the y-intercept of a rational function by substituting a 0 in for x and then solving. So basically what you want to do is you want to find f of 0. Sorry, that should be f of 0, not x. So it's just like any function. If you put a 0 in for x, you're going to find the y-intercept. If you put a 0 in for y and solve for x, that's how you find the x-intercepts. The next thing you want to find is your x-intercepts. The x-intercepts are when the rational function is equal to 0. So I want to know when the rational function is equal to 0. And we know a fraction is equal to 0 when the numerator of the fraction is equal to 0. So in order to find the x-intercepts, all you need to do is find the x-intercepts of the numerator's polynomial function. Other things that we can have in our graph are holes. We have potentials for holes in our graph when we have common factors in the numerator and the denominator. So anytime I have a common factor, I could end up with a hole in my graph. Now, if the factors are not repeated anywhere else, I'll definitely have a hole, but if they may be repeated, we can end up with our vertical asymptotes. Vertical asymptotes are when the denominator of the simplified rational function, after I cancel out my common factors, it's when that denominator is equal to 0. So I have vertical asymptotes when d sub x is equal to 0, provided that my rational function is in simplest form. And the last thing we want to do is we want to discuss the end behavior of my rational function, of our rational functions. And the way we analyze the end behavior is we take the leading term and we divide it by the leading term. So the leading term of the numerator divided by the leading term of the denominator. And what you can do is you could actually look at the degree of the numerator over the degree of the denominator. Remember, our simplest rational function is f of x equals 1 over x. Well, what's the degree of the denominator? 1. What's the degree of the numerator? 0. And we know that this graph looks something like this. We also know what the graph of f of x equals 1 over x squared looks like. This is x, this is y. Notice for both of these, as x's get very, very big and very, very small, I have a horizontal asymptote at 0. So in general, when I'm going to call n is equal to the degree of the numerator, I'm going to call d the degree of the denominator. In general, anytime when d is greater than n, you are going to have a horizontal asymptote at 0. And it's when at y equals 0. We always give them equations of lines. Well, let's look at some other simple rational functions. Well, if I have x over x, I told you we want to do leading term over leading term. Well, what's that divided by that? Well, it's 1. Or I can have 3x squared over 2x squared. 3x squared divided by 2x squareds, the x squareds cancel, and I'm left with 3 over 2. So any time that the degree of the denominator is equal to the degree of the numerator, you are going to have a horizontal asymptote at the leading coefficient of your numerator over the leading coefficient of your denominator. The last possible example that I have, we have it with the denominator is greater than the numerator, denominator is equal to the numerator. Well, what if the numerator is greater than the denominator? For example, x squared over x. Well, if I do x squared over x, that simplifies to x. And as x gets very, very big, y is going to become very, very big. Okay, this is x when x is not equal to 0. Remember, we can't divide by 0. Basically, the end behavior is based off of what that's going to look like. Well, that is the function, the graph of our identity. So this graph right here is actually going to follow along the line y equals x as x gets very, very big. And actually, this is the graph for it. It's x when x is not equal to 0. So anytime that the degree is above, it's going to increase or decrease without bound. Okay, for example, if I have 3x cubed over 2x to the first power plus something, this would simplify, if I'm looking at it, as 3 halves x squared, and we know what the x squared graph does as x gets very, very big. The x squared graph goes up without bound at each end, so we would not have an asymptote for this case. It would increase like the x squared function as x gets very, very big. The special case is when the numerator is exactly 1 above the denominator. You are going to end up with an oblique asymptote. And you find the equation for the oblique asymptote by doing the polynomial division of the numerator divided by the denominator. So, if the numerator is degree of the numerator is greater than the degree of the denominator, you are either going to have an oblique asymptote, and you're going to get that if n is equal to d plus 1. Or you're going to end up with no asymptote. And you're going to get that if n is greater. So you're going to end up with an oblique anytime this is more than 2. More than 1. So if n is greater than d plus 1. So our 3 possible cases for end behavior, again, horizontal asymptote at 0, a horizontal asymptote at some constant number of leading coefficient divided by leading coefficient, an oblique asymptote if the degree of the numerator is 1 more than the denominator, or no asymptote where the end behavior follows what the graph of a polynomial function would be at a higher degree term. So these are the key pieces of information that we want to know for rational functions. So in order to get to do stuff with rational functions, our goal is to write the numerator in factored form, write the denominator in factored form, and that gives us all the information that we need to conduct a rough sketch of the graph of the function.